Hi there again. These are the notes for lesson 2.2b. If you are looking for these notes, they are actually in the 2.3 document, the notes document, because it all just kind of flows in together. And so it's not in the 2.2 notes. This is part of your 2.3 notes. Should be right after what you finished writing in class yesterday. So today we're going to talk about one-sided derivatives. That means derivatives from the left versus from the right. And so we've kind of talked about that before as it deals with limits. And then differentiability, checking from the left and the right. So in order for a function to be differentiable, you have to check the limits and the derivative. So remember, when we checked our one-sided limits, we checked the limit as x approaches a from the left of f of x, and we had to check the limit as x approaches a from the right of f of x, and we also had to check the closed point f of a. And all three of those should have been equal to the same number, which we call the limit. This part of checking f of a is a part that often gets skipped. People forget that they have to check that center point to make sure it's not removable. Once you've checked those things, then you can move on and check the one-sided derivatives. And in a derivative, you're still checking approaching a from the left, but this time you're checking f prime. And then you would also check the limit approaching a from the right of f prime. And the two of those things should be equal to the slope value m. So for checking the limits, there are three pieces to check that all have to be equal to L. But for derivatives, there's only two pieces to check, and they need to be equal to the same value of m for the slope. So if you're given a piecewise function like this, where it's defined in two different domains, a domain less than 0, that's the left, and a domain greater than 0, that's the right side, you want to check to see if this is called differentiable. So there are 5 things to check. There are 2 limits and f of 0 itself. So 1, 2, 3. And once you pass those 3, if all 3 of those are equal, then you can check 4 and 5 for the left and right hand derivative. Okay, so let's check the left hand limit. So we want to check the limit as x approaches 0 from the left. And when we do, we'll be using the function negative x. So we're going to put in negative 0 minus. Those are both two negative numbers. They cancel each other out. We get 0. We'll check the right-hand limit. So we're going to check the limit as x approaches 0 from the right. And when we do the right side, we use the function x. So we'll plug 0 plus into that, and 0 plus is a positive number. So far, the left-hand limit and the right-hand limit equal each other. And then we want to check f of 0 itself. F of 0, the equal to part, is right here, which means I'm going to use the same equation that I did for the right side. And so I will plug 0 in, and I get 0. And so all 3 of those things match, and so we say that L equals 0 then, because the first, the second, and the third ones all matched. Now I'm going to move on to the left-hand derivative. So I'm going to take the limit as x approaches 0 minus, and now I need to take the derivative of negative x. Negative x is the constant multiplier rule. we understand that there's a negative 1 right there. And so the derivative of that, of negative 1x, is just the value negative 1. And that's a constant, and so we get negative 1. The right-hand derivative, as I approach 0 from the right, I will be taking the derivative of that. And that's also a constant multiplier because we understand that there's a number 1 right there. And so that slope is 1, or derivative is 1. Okay, so that's equal to 1. Now these two things do not equal each other. The slope from the left did not equal the slope from the right. And so then we make the conclusion it is not differentiable. You have to be equal to be differentiable. So the conclusion is, if you have step 1 equal to step 2 equal to step 3 and all equal to L, but step 4 and step 5 are not equal to each other, that's called, and we just used that word, non-differentiability. Okay, non-differentiability. When the first 3 of the limits all match, but the derivative limits do not. So let's try this question. Show the function is not differentiable. So we're going to go through the steps 1, 2, and 3, and then we'll move on to steps 4 and 5. So first we want to find the limit as x approaches 0 from the left. From the left we'll be using the cubic term. And when I plug 0 in, that's 0 minus cubed, which is still 0 minus. I'm going to check it from the right. So x approaches 0 plus. From the right, I'm going to use 4x. So 4 times 0 plus, which is still 0 plus. And 0 minus and 0 plus are equal to each other. They're both approaching 0. And then I'm going to try f of 0 itself. And this time, the equal to is up here, so I'll be using the cubic. So that would be 0 cubed, which is still 0. And so check 1, check 2, check 3. The limit equaled 0, the value of L. Now I'm going to check the derivatives. So the limit as x approaches 0 of, and now I want to find the derivative of the left piece. And using our power rules, the derivative is move the 3 to the front and decrease the power. All right, we'll plug 0 into that, so 3 times 0 plus squared, that will be 0 positive. Now I'm going to find the limit on the right. So x approaches 0 from the right. This time I want to find the derivative of the right-hand piece. And the right-hand piece is 4x. Now that's a constant multiple. And so the derivative of that is 4. And since that's a constant, the answer is 4. So since 0 plus and 4 are not equal to each other, then we have shown, since 0 is not equal to 4, then we have shown it is non-differentiable. All right, so to summarize, if f has a derivative, that means differentiable, yes. That means you've shown it to be differentiable. Then f is continuous at a. That means that all 5 pieces, all 5 parts of the definition are true, invalid. Okay, so if you've gotten to the derivative, that means that you've gotten through all 5 pieces, and so it's continuous and differentiable. But if you switch that around, that is not true. So if f is continuous, what if we do that first? Then the question is it guaranteed to be differentiable? So this is a good true-false question that you could get asked. If f is continuous, is it guaranteed to be differentiable? And the answer is no. It may or may not. But you can't guarantee it. All right, you might get through the first 3 requirements, but not get through 4 and 5. Okay, so if f is continuous, all you know is that you've gotten through the first 3. You don't know if requirements 4 and 5 are going to work. But if you say it this way, if f is differentiable, or if f has a derivative, then you know you've gotten through all 5 of the requirements, and so you can assume that it is continuous. Okay, so differentiability implies continuity. That's the title of this slide. But continuity does not imply differentiability. It might be differentiable, but it might not. And so that's not a guarantee. Differentiability implies continuity, but continuity does not imply differentiability. All right, so find the constants that would make this be differentiable. So we need to get through the first, all 5, in order to make this be differentiable. And we're going to do it with letters and not just necessarily numbers. So let's get through the first 5. Okay, so I need to do the limit as x approaches, and it's at 3 where I'm concerned. Okay, so I'm going to approach 3 from the left. I'm also going to approach 3 from the right, and I'm going to do f of 3. So those are the first 3 requirements, that I'm going to set up. When I do 3 from the left, I'll be using k rad x plus 1. When I do 3 from the right, I will be doing mx plus 2. And when I do f of 3, okay, I need to figure out where it's equal to 3, and it's equal to 3 right here. So I'll be also using the k times x plus 1. The square root, I mean. Okay, so we're going to substitute the number 3 in for x. So I'll plug in 3 negative, 3 minus, I'll plug in 3 plus, and I'll plug in 3. So this will give me k times the square root of 3 minus plus 1. And then this will give me 3m plus 2. And this will give me k times the square root of 3 plus 1. So let's simplify each of those. This is k times the square root of 4, which is 2k. 3m plus 2 is already simplified, and this will be k times the square root of 4 minus, which is k times 2 minus, or 2 minus times k. And we really don't need to include the minus once we get to the end there. So 2 of them worked out to be 2k, and 1 of them worked out to be 3m plus 2. And these all have to be equal to each other. So 2k has to be equal to 3m plus 2. All right, all of these have to be equal to each other. All right, now let's do the differentiability part. So maybe I'll just draw a line down here or something. All right, to do the differentiability part, we're going to check the limit as x approaches 3 minus, and we'll check the limit as x approaches 3 plus. When I do 3 minus, I need to do the derivative of the left side. Now before I do that, I need to rewrite. Okay, so let's work on a rewrite a minute. And I'm going to have a k with parentheses, x plus 1, and then I'll have a half. The reason I have to rewrite that is so that I can use the power rule, so that I can pull the 1/2 out to the front, and I can minus the 1 from it. So my rule will then get me 1/2 in front of k, and x plus 1 is now to the negative half power. For my second derivative, I'll be doing the derivative on the right, so it'll be the derivative of this. mx is a constant multiplier, and so the derivative of that is m plus, and then 2 is a constant, so m plus 0. And so I have the answer to this. If I plug 3 now into, I'm going to plug 3 into x, and there's nowhere to plug 3 into because there's no x's left, so the answer to this is m. And the answer to this will be 1/2 k, and then 3 plus 1 to the negative 1/2. So we'll keep going with that. That's 1/2 k times 4 to the negative half. And I got to rewrite this back in its regular form. 1/2, the k is on the top, and the 4 is on the bottom under a square root. So that's 1k on top and 2 times 2 on the bottom, which is k over 4. And from all of that, we know that those two things have to be equal. And so m must be equal to k over 4. So what did we end up with? We ended up with 2k equals 3m plus 2, and m equals k over 4. We can use those two things to solve each other, so you'll probably want to go on to the next blank slide here. If m is equal to k plus 4, then I can substitute that into this m position. So I'm going to solve this using substitution. So 2k equals 3, and then in place of m, I'll replace it with k over 4 plus 2. In other words, 2k equals 3/4 k plus 2. Now mathematically, I don't like the number 4 as a denominator, so I can multiply each term by 4. So I'll multiply this by 4, and this by 4, and this by 4. The 4's by the k cancel out. So I'll be left with 8k equals 3k plus 8. Then I'll subtract 3k from both sides. So 5k equals 8. So k is 8 over 5. But then what does that make m? Remember up here that m is k divided by 4. So if m is k divided by 4, That's the same thing as 1/4 k. And if I now know that k is 8/5, then I'm going to have 1/4 times 8/5, which is 8/20, which reduces to 2/5. And so the answers to this question are that k has to be 8/5 and m has to be 2/5 in order for this problem to be both continuous and differentiable. So I did continuous first, and I got a conclusion. Then I did differentiable second, and I got another conclusion, and then I combined those two together because they both have to be true. And I substituted one in for the other to solve. So that's kind of a heavy-duty question. Right, that's gonna take the most brain power and the most work for you in terms of differentiability. All right, I hope you have a great weekend. Enjoy having Friday off, and I will see you guys back together on Monday.